This is my submission for take-home test 3. For the first part, we need to find these three resistances, RS, RG, RD. We know that the NMOS is used as an amplifier, which means it operates in the saturation region. So we know the equation for ID, and we know the value of ID, which is 0.4 milliamps. So we can plug in ID as well as Kn, which is given, to find VOV, which should be 0.4 volts. Using VOV, we can use this equation to find VGS and plug in VT, and VGS is 1.2 volts. And from there, we can use this KVL, plug in the voltages, as well as VGS and ID to find RS, which is 9.5 kilo ohms. For RG, drawing the small signal model, we can see that RG is equal to RI, and we are given RI, which is 10 mega ohms. So RG is also equal to 10 mega ohms. And for the last resistor, RD, we have to use the max signal swing plus or minus 0.8 volts at the drain. And we can look at the equation VDS is greater than or equal to VOV, which means this is the equation for the saturation, to stay in saturation region, which means that VDS should be greater than or equal to VGS minus VT, and VT is equal to this 0.8 volts. Separating VDS and VGS into separate parts, we can cancel the VS part, and we get this inequality now. And to approximate VD, we can assume that VGS or VG is constant and doesn't change, or that means that VOV also doesn't change. Even though this isn't quite true, we can use it to approximate. And so we get this inequality here. We can plug in this VD value for the AC part to find that VD, the DC part, equals 0 volts in that region to stay in saturation. So this is the point, the minimum VD DC value that it can have to stay in saturation and not go into the triode region. And so using this 0 volt value for VD, we can plug it in here and use this KVL 5 volts minus VD, so 5 volts minus 0 volts. And we already know ID, and then we can use those values to find RD, which equals 12.5 kilo ohms. For part B, we're finding GM and RO. We are given these equations in class, so GM equals 2ID VOV. Plug in the values that we found in part A, and we get that GM is equal to 2 milliamps over volts. And then for RO, another equation given in class, 1 over lambda times ID, and lambda is equal to 1 over VA. We are given VA, and so RO is equal to 100 kilo ohms. For part C, terminal C is grounded, so the source is grounded. Terminal A is a signal, and V out is here at B, and we're given all these other values. So we're supposed to find A, which is the voltage gain of the circuit, and that is equal to VI over V sig times V out over VI, or that is also equal to this equation here. And we can find, we know all these values for Ri and our signal, and then AV, the voltage gain of the amplifier, is this equation. We know RL and RO. I calculated RO, big RO here, which is small RO in parallel with RD, and that's equal to 11, around 11 kilo ohms. And AV is equal to this times the open loop gain, and that's this equation here. This is for common source, negative GM times RD in parallel with RO. And so plugging in all of these values, which we have already calculated both here and here, we can basically just plug in everything into this equation and eventually get that A is equal to negative 9.569 volts over volts. For part D, we use almost all the same equations except for now to calculate big RO, it's 1 over GM in parallel with RS and in parallel with RO, and so we have a different RO value because now the drain is grounded, so this is common drain. And then we have different equations for the open loop gain also, which is given here. But we can, similar as before, just plug in these values into these equations. That's the same equation for AV as well as A, only the open loop gain equation as well as RO has changed. But after plugging in all of those values into the equations, we get that A is equal to 0.820 volts over volts. For part E, we are now given V signal, which is this equation here, and we have to draw the waveforms for all of these values. So I drew out V signal here first, so this has a frequency of 2 kilohertz. Found the period here, which is 500 microseconds, and we know that the peak value of this is 0. Sorry, you can't really see that right there, but 0.01, which is this value here. And so to find V out, we already calculated the voltage gain of the circuit A, and so we can just simply find V out by plugging that in, and we see that the peak value will be equal to 0.0956, which is this 9.569 times this peak value. And this V out will be flipped in terms of, because of this negative sign here. So it has the same period, but it's just been flipped and has different peak values. For VD, the DC value of VD we calculated before was 0 volts, and we were given the max signal swing of plus or minus 0.8 volts. So this is at 0 right here, and then this is the signal swing. And for VS, there's no AC value because for this portion we're using the same circuit in part C, so that means that the source is grounded. So that means there is no AC power, or it's equal to 0 volts basically. And then so there's only this DC VS is equal to negative 1.2 volts, so it's a constant line like this. And for the last part, ID, we are given the DC value, which is 0.4 milliamps or 400 microamps. And to calculate the AC ID value, we can use GM times VGS, and VGS is equal to VI. If we look at the small signal model, this VGS is equal to VI, this voltage here. And VI is equal to RI over RI plus R sig times V signal. And we already know these values for RI and R signal. Plug those in, and we can see that this ID is equal to 1.8 milliamps times V signal. If we look at the peak for V signal, it's that 0.01 volts. Multiply that by 1.8 milliamps, and the peak of the ID value will be 18 microamps. And so the AC value will go swing this way with a plus and minus 18 microamps that is offset by this DC value of 400 microamps. Thank you.